What if I told you the very first molecules in the universe are still whispering their secrets to us across billions of years? These primordial building blocks, tiny, fragile, and forged in the aftermath of the Big Bang, hold the missing pieces to one of science's greatest puzzles: how our cosmos transformed from a seething, chaotic fireball into the structured, star-filled expanse we see today. Picture this: the universe was once so hot and dense that atoms couldn't even exist. But when the first molecules finally emerged, they set off a chain reaction that would shape galaxies, stars, and eventually us. For decades, scientists believed the earliest molecules were simple, almost boring, little more than hydrogen atoms pairing up. But what if the truth is far stranger? New discoveries suggest these ancient chemical bonds might have been more complex, more elusive, and far more influential than we ever imagined. They could be hiding in the faint glow of distant nebulae, etched into the oldest stardust, or even lurking in the cold voids between galaxies. And if we can decode their stories, we might finally understand how the universe took its first breath, and how everything we know came to be. This isn't just about chemistry or distant cosmic history. It's about tracing our own origins back to the very beginning. Every atom in your body, every breath you take, every star you see at night, it all connects to those first fragile molecules. So let's embark on a journey to uncover their mysteries. From cutting-edge telescopes peering into the past to lab experiments recreating the conditions of the infant universe, we're piecing together a saga 13.8 billion years in the making. And what we're finding might rewrite everything we thought we knew. The universe didn't start with stars or galaxies. It began with something far smaller and quieter: the humble hydrogen molecule. Just minutes after the Big Bang, as the cosmos cooled from a roiling sea of plasma, the first chemical bonds flickered into existence. These weren't the complex molecules we know today, but simple pairs of hydrogen atoms clinging together in the sparse, cooling void. Think of them as the universe's first whispered conversation, a fragile handshake between particles in an otherwise chaotic infancy. Hydrogen's simplicity is what made it so revolutionary. With just one proton and one electron, it was the easiest atom to form, and when two of them linked up, they became the building blocks for everything else. But here's what's wild: without these tiny molecules, the universe might have stayed a featureless fog of gas. Hydrogen acted like a cosmic coolant, allowing dense pockets of gas to collapse under gravity's pull. Those collapsing clouds, they were the birthplaces of the very first stars, igniting the darkness and lighting the fuse for everything that followed. Picture stellar nurseries like the Orion Nebula, those swirling, glowing clouds where new stars are born. Those vibrant scenes owe their existence to hydrogen's quiet dominance. Even today, over 90% of the atoms in the universe are hydrogen, a staggering reminder of its primordial legacy. But what's even more fascinating is how these molecules shaped the cosmic timeline. By helping gas clouds condense and heat up, they set the stage for nuclear fusion to kickstart inside stars, forging heavier elements like carbon, oxygen, and iron, the very ingredients that would one day make planets, oceans, and life itself. Yet for all its importance, hydrogen is deceptively elusive. It doesn't glow brightly like neon or form dramatic dust lanes in space. Detecting it requires peeling back the layers of the cosmos with radio telescopes, catching the faint whispers of molecular vibrations that have traveled billions of years to reach us. And when we do, we're not just studying chemistry, we're eavesdropping on the universe's first recipe, written in a language of bonds and vibrations that still echo through the voids of space. But hydrogen wasn't alone in those early moments. There was another player waiting in the wings, a molecule so elusive that scientists debated its existence for decades. Meet helium hydride, a fragile union of helium and a hydrogen ion, often written as HEH+. This odd couple might sound like a footnote in chemistry, but it's actually a leading contender for the title of the very first molecule in the universe. Here's why that matters. While hydrogen molecules needed slightly cooler conditions to form, helium hydride could have emerged earlier in the searing heat of the universe's infancy, when temperatures were still too extreme for anything else to survive. Detecting helium hydride today is like finding a fossil from the universe's first second. In 2019, astronomers finally spotted its signature in a planetary nebula called NGC 7027 using the airborne SOFIA telescope. But here's the twist. This detection wasn't in some ancient corner of the cosmos. It was in a relatively modern stellar graveyard, raising questions. If helium hydride truly existed in the primordial universe, why is it so hard to find now? The answer lies in its fragile nature. Back when the universe was just a few 100,000 years old, helium hydride acted like a cosmic bridge, helping to cool the seething plasma and pave the way for hydrogen molecules to take over. But once its job was done, it essentially vanished, broken apart by ultraviolet light or swallowed by the formation of heavier elements. This leads to a fiery debate among scientists. Some argue helium hydride was a fleeting spark, too rare and short-lived to leave a lasting impact. Others believe it was the unsung architect of cosmic chemistry, setting the stage for everything that followed. To settle this, researchers have recreated the conditions of the early universe in labs, zapping mixtures of hydrogen and helium with lasers to mimic the intense heat of the Big Bang's aftermath. What they've found is astonishing. Even in those brutal conditions, helium hydride forms and survives long enough to kickstart reactions that would eventually build the first stars. So why hasn't it been detected in the distant, ancient universe yet? The challenge is that primordial helium hydride would emit faint signals at very specific wavelengths, drowned out by the cosmic microwave background or masked by intervening dust. New telescopes like the James Webb Space Telescope are hunting for these whispers, peeling back time to an era when the universe was still learning how to build molecules. If they succeed, it would be like uncovering the first brushstrokes on the canvas of creation, a glimpse into the moment chemistry itself was born. Whether hero or bystander, helium hydride's story forces us to rethink the universe's earliest chapters. It's a reminder that even the smallest, most fragile bonds can alter the fate of everything. And if we're right about its role, this humble molecule didn't just witness the dawn of chemistry, it helped write the recipe for the cosmos. Hydrogen molecules might not be flashy, but their quiet persistence reshaped the universe. While helium hydride stole the spotlight in the earliest moments, neutral hydrogen molecules, just two hydrogen atoms bound together, were the steady workers that built the cosmos we know. Here's how it happened. As the universe expanded and cooled further, protons and electrons finally slowed enough to form complete hydrogen atoms. But it took another 100 million years for these atoms to gingerly link up into pairs, creating the first stable H2 molecules in the cosmic dark. What made H2 so special was its ability to survive. Unlike fleeting helium hydride, which quickly broke apart, molecular hydrogen could linger in the cooling gas, acting like a cosmic refrigerant. By radiating away heat through subtle vibrations, these molecules allowed dense pockets of gas to shed energy and collapse, a critical step in forming the first stars. Imagine a simmering pot of soup suddenly chilling in just the right spots, creating swirls where ingredients clump together. That's essentially what H2 did for the primordial universe, turning a uniform haze into a tapestry of dense knots primed for stellar birth. But spotting these ancient molecules isn't easy. They don't shine like stars or glow like neon. Instead, they reveal themselves through faint infrared signals or the way they absorb light from distant quasars. In 2018, astronomers detected H2 in a galaxy so far away its light took nearly 13 billion years to reach us, a relic from the era when the first stars were just flickering to life. The discovery was like finding a fossilized raindrop from the dawn of time, proof that these unassuming molecules were the invisible scaffolding for cosmic structure. Yet the story isn't just about detection, it's about competition. Some theories suggest other molecules like lithium hydride or even water could have formed earlier. But none matched hydrogen's perfect balance of abundance and stability. Lithium was too rare and water required oxygen, which didn't exist yet. H2, by contrast, was everywhere, a humble overachiever that turned the universe's chaos into order, one bond at a time. Today, we're still uncovering its secrets. Advanced simulations show how molecular hydrogen's cooling effects created the first proto-galaxies, lumpy, misshapen things that bore little resemblance to the majestic spirals we see now. And in labs, scientists replicate those primordial conditions, watching as hydrogen molecules form in vacuum chambers chilled to near absolute zero. Each experiment, each observation, peels back another layer of this silent revolution, reminding us that sometimes the quietest players write the most epic stories. When we think about the universe's first molecules, lithium rarely gets the spotlight, yet this lightweight element might hold one of the most puzzling clues in cosmic chemistry. Here's why it's so intriguing. According to the Big Bang theory, lithium was one of the few elements forged in those initial chaotic minutes, alongside hydrogen and helium. But there's a cosmic detective story here. Observations show the universe has about 3 times less lithium than our calculations predict. Where did it go? Some scientists suspect lithium didn't just vanish. It might have been locked away in early molecules we've yet to fully understand. Enter lithium hydride, a speculative but tantalizing candidate for the first molecular bonds. Picture this: in the universe's first few 100 million years, as temperatures dipped below 3,000 degrees, lone lithium atoms could have paired with hydrogen ions, forming fragile lithium hydride molecules. These bonds would have been far rarer than hydrogen or helium hydride, given lithium's scarcity, but they might have played an outsized role. Unlike helium hydride, which broke apart easily, lithium hydride could have survived longer in certain pockets of the early cosmos, acting as a catalyst to cool gas clouds or even shield other molecules from destructive radiation. The challenge is proving it. Lithium hydride leaves almost no detectable trace in modern space, and recreating its formation is a nightmare for lab scientists. It requires unthinkably low temperatures and near-perfect vacuum conditions akin to trying to capture a snowflake in the heart of a volcano. Yet in 2020, researchers in Germany mimicked these primordial conditions using supercooled magnetic traps, observing how lithium and hydrogen could indeed form fleeting bonds. The kicker: these molecules absorb and emit light at very specific wavelengths, offering a potential fingerprint for astronomers to hunt, but the plot thickens. Some models suggest lithium hydride wasn't just a passive player. It might have helped jumpstart the formation of the first stars. By radiating away heat more efficiently than hydrogen alone, these molecules could have accelerated the collapse of gas clouds, igniting stellar nurseries earlier than we thought possible. Others argue lithium was simply too rare to matter, its contributions lost in the noise of hydrogen's dominance. The real mystery, though, isn't just where lithium hydride existed, but where its descendants might be hiding. Could traces of these ancient molecules linger in the atmospheres of the oldest stars, or in the frigid depths of interstellar space? Telescopes like the James Webb are now scouring the cosmos for these whispers, hoping to solve a riddle that's persisted since the first atoms shook hands. If they succeed, it wouldn't just fill a gap in our periodic table, it would rewrite the first chapter of cosmic chemistry. Until then, lithium remains the universe's quiet rebel, defying expectations and daring us to look closer. Deuterium might sound like an obscure footnote in chemistry, but this heavy hydrogen variant could be the unsung hero of cosmic chemistry. Unlike regular hydrogen with just one proton and one electron, deuterium packs an extra neutron in its nucleus, making it slightly heavier and far more powerful in its influence. In the early universe, this subtle difference meant deuterium could form bonds more easily, acting as a molecular glue when ordinary hydrogen was too flighty. Picture a chaotic dance where deuterium was the partner who kept things steady, allowing more complex reactions to take shape in the swirling cosmic gas. The magic happened in the cold. As the universe expanded and cooled, deuterium's stability let it team up with hydrogen to form hydrogen deuteride, a simple molecule with profound consequences. This pairing didn't just drift idly, it became a stepping stone to even heavier molecules. Modern theories suggest that hydrogen deuteride's vibrations helped dissipate heat from collapsing gas clouds, accelerating the birth of the first stars. But here's where it gets even more fascinating. Deuterium might hold the key to how water, the essence of life, came to exist. Meteorites older than Earth itself carry isotopic fingerprints of deuterium-rich water, hinting that this heavy hydrogen was already weaving itself into cosmic chemistry long before our solar system formed. In labs, scientists simulate the icy conditions of interstellar space, watching as deuterium atoms latch onto oxygen to form heavy water molecules even in the harshest environments. These experiments suggest that deuterium didn't just participate in the universe's chemistry, it turbocharged it. Yet deuterium's story isn't just about the past. Astronomers now hunt for its signals in distant gas clouds, where its unique spectral lines act as cosmic breadcrumbs tracing the evolution of molecules across billions of years. Each detection peels back another layer of this isotope's hidden influence, proving that sometimes the smallest differences, like a single neutron, can tip the scales of cosmic history. Now let's venture into one of the most radical theories about the universe's first molecules, one that turns our entire understanding of cosmic chemistry on its head. What if those initial molecular bonds didn't form through conventional cooling and particle collisions, but instead bubbled into existence from the chaotic quantum foam of spacetime itself? This isn't science fiction, it's a fringe but fascinating idea gaining traction among physicists who study the universe's first fleeting moments. Picture the infant cosmos not as a smooth, expanding fireball, but as a seething ocean of quantum fluctuations. At scales trillions of times smaller than an atom, space and time weren't orderly. They frothed like a boiling pot, with virtual particles popping in and out of existence in a frenzy of energy. In this quantum foam, pairs of particles could spontaneously emerge, borrow energy from the vacuum, and then vanish almost instantly. But here's the twist. Some theorists propose that under the extreme conditions of the early universe, these fleeting quantum bubbles might have stabilized just long enough to form the first proto-molecules, exotic, unstable bonds that defied the usual rules of chemistry. Think of it like soap bubbles clinging to each other in a frothy sink. Most pop immediately, but occasionally, a few merge into something more complex before dissolving back into the foam. In the quantum realm, these transient interactions could have created bizarre molecular structures like hydrogen atoms linked by a temporary warp in spacetime, or particles entangled across dimensions we can scarcely imagine. These wouldn't be the sturdy H2 molecules we know today, but ghostly precursors, here one instant and gone the next, yet somehow leaving a fingerprint on the universe's evolution. Detecting such ephemeral molecules is a nightmare with current technology, but clues might lie in the cosmic microwave background, the faint afterglow of the Big Bang. Some models suggest quantum foam interactions could have imprinted subtle irregularities in this radiation, like ripples from a stone tossed into a pond. Others argue these early fluctuations seeded the density variations that later birthed galaxies, meaning the universe's large-scale structure might trace back to these phantom molecules. Not everyone's convinced, of course. Critics point out that quantum foam effects are typically negligible outside black holes or particle colliders, hardly the environment for nurturing chemistry. But supporters counter that the early universe was a black hole, a singularity where all known physics breaks down. If they're right, we might be missing a whole chapter of molecular history, erased by time but still echoing in the quantum static of space. Whether this theory holds up or not, it forces us to ask a deeper question. What really counts as a molecule? If bonds flickered into existence without atoms ever truly touching, does that redefine chemistry itself? The quantum foam conundrum reminds us that the universe's first moments were stranger than we can fathom, and that the story of its molecules might be wilder than we dare imagine. Cosmic dust might seem like an afterthought, tiny specks adrift in the void, but these microscopic grains could be the unsung architects of the universe's first complex molecules. Picture a frigid, barren expanse in the early cosmos, where drifting particles of silicate and carbon floated like cosmic sand. Too small to see, yet vast in number, these dust grains became something extraordinary: molecular workshops. Here's how it worked. In the emptiness of space, lone atoms rarely collide with enough energy or the right orientation to form stable bonds, but dust grains changed the game. Their surfaces acted like microscopic dance floors where atoms could latch on, slow down, and finally hesitantly shake hands. Silicate grains, in particular, were the ultimate matchmakers. Their crystalline structures offered nooks and crannies where hydrogen, carbon, and oxygen atoms could gather, shielded from the harsh radiation that would otherwise tear them apart. Experiments here on Earth have recreated these conditions in vacuum chambers, chilling dust analogues to near absolute zero, and watching as molecules like water and formaldehyde assemble on their surfaces, atom by atom. It's chemistry at its most primal, no fiery stellar nurseries, just the quiet patience of cold, dark space. But the real magic happened when these dust-laden molecules got caught in the whirlpools of protoplanetary disks. Imagine a young star, its birth shrouded in a spinning disk of gas and dust. Within that chaos, icy grains coated in molecular layers collided, stuck together, and grew into larger aggregates. Heat from the newborn star baked these dirty snowballs, driving chemical reactions that cooked up everything from simple methanol to the amino acid glycine precursors to life's building blocks. Astronomers have spotted these molecular factories in action. The Atacama Large Millimeter Array has captured infrared fingerprints of complex organics clinging to dust in distant star-forming regions, while the James Webb Space Telescope peers into the hearts of protoplanetary disks, revealing how chemistry evolves from simple ices to intricate compounds. These observations suggest that cosmic dust didn't just host molecules, it amplified their complexity, turning the universe from a chemical desert into a fertile playground. Yet the story isn't just about what dust created, it's about timing. Some models suggest surface chemistry on grains could have accelerated molecular formation even before the first stars ignited, meaning the recipe for life's ingredients might have been written in the cold, dark stretches between galaxies. Others argue dust's role was local, a late bloomer in cosmic history. Either way, it forces us to reconsider where and how the universe's first chemical experiments truly began. So next time you see a streak of dust caught in sunlight, remember, those mundane motes might hold the secret to how chaos became chemistry and how stardust eventually learned to dream. Dark matter doesn't play by the rules of ordinary chemistry. It doesn't form bonds, emit light, or even interact with the atoms that make up stars and planets. Yet this invisible cosmic scaffolding might have been the silent architect behind the universe's first molecules. Picture a vast, pitch-black sea where dark matter's gravitational pull sculpted the primordial gas into dense pockets, creating the perfect nurseries for molecular chemistry to ignite. Without it, hydrogen and helium might have drifted forever in a featureless void, too sparse to collapse into the stars that forged heavier elements. The key lies in dark matter's ability to warp space itself. In the early universe, clumps of dark matter acted like gravitational anchors, tugging ordinary matter into swirling filaments and halos. These structures provided the high-pressure environments where atoms could collide and stick, first as simple pairs, then as complex chains. Some models suggest that dark matter's influence didn't stop there. Hypothetical particles like weakly interacting massive particles, or WIMPs, might have occasionally bumped into hydrogen atoms, transferring just enough energy to kickstart molecular formation in regions otherwise too cold or diffuse. But here's the twist: dark matter's role wasn't always constructive. In certain scenarios, its gravitational tugs could have torn apart fragile molecular clouds before they fully coalesced, creating a cosmic tug-of-war between creation and destruction. Astronomers studying ancient quasars have spotted puzzling gaps in the distribution of early molecules' voids that might trace back to dark matter's disruptive fingerprints. Others argue these voids were actually dark matter's greatest gift, preventing gas from collapsing too quickly and allowing molecules to stabilize in the resulting turbulence. The wildest theories propose dark matter wasn't entirely passive. If a fraction of it decayed or annihilated, the resulting bursts of energy could have heated surrounding gas, delaying star formation just long enough for complex chemistry to take root. Imagine a cosmic timer where dark matter's faint decay ticked away in the background, pacing the universe's transition from simplicity to complexity. While we can't yet detect these shadowy interactions directly, clues might hide in the echoes of the cosmic microwave background or the skewed distribution of distant hydrogen clouds. Future telescopes like the European Space Agency's Euclid mission could map dark matter's hidden structures with unprecedented precision, revealing whether they align with the birthplaces of the first molecules. Until then, dark matter remains the universe's most elusive collaborator, a ghostly hand guiding chemistry's first steps without leaving a single atom behind. The birth of the first stars didn't just light up the cosmos, it unleashed a storm of ultraviolet radiation so violent it could tear molecules apart atom by atom. This was reionization, the universe's fiery adolescence, when starlight ripped through the primordial fog, stripping electrons from atoms and turning calm molecular nurseries into zones of chaos. For those fragile first molecules, hydrogen, helium hydride, lithium compounds, it was like standing in the path of a cosmic hurricane. Simulations of this era paint a brutal picture. As massive early stars flickered to life, their UV photons blasted through surrounding gas clouds with enough energy to break molecular bonds in nanoseconds. Hydrogen molecules, which had spent hundreds of millions of years quietly cooling the universe, were suddenly ionized back into solitary atoms. Helium hydride, already clinging to existence by a thread, vanished entirely from vast regions of space. The violence wasn't random, it created a patchwork of destruction. Dense pockets of gas shielded some molecules, while exposed regions were scoured clean, leaving behind a chemical wasteland. Yet this destruction had a strange silver lining. The same radiation that tore molecules apart also energized their surroundings, triggering new reactions in the wreckage. Ionized hydrogen atoms, now hyperactive from UV exposure, collided with dust grains or other atoms at unprecedented speeds. These chaotic encounters birthed molecular ions like H3+, a triatomic hydrogen ion that became the backbone for more complex chemistry. Think of it as a cosmic recycling plant. The first stars didn't just erase molecules, they forced them to evolve. Astronomers see echoes of this epoch in distant quasars, whose light cuts through ancient gas clouds like a forensic probe. Absorption lines in their spectra reveal ghostly traces of molecules that survived reionization's wrath, clinging to existence in shadowy galactic outskirts. Meanwhile, lab experiments recreate the frenzy with plasma chambers and UV lasers, showing how even under siege, simple molecules find ways to persist or adapt. The twist: without this turbulent era, the universe might never have graduated to richer chemistry. reionization's violence cleared the stage for heavier elements forged in stellar cores, allowing carbon, oxygen, and nitrogen to eventually take center stage. It was a trial by fire, one that set the cosmic clock ticking toward everything we know today. The early universe wasn't just hot, it was a roiling plasma, a seething ocean of charged particles where even atoms couldn't hold themselves together. For nearly 400,000 years after the Big Bang, protons and electrons raced through this scorching soup, too energetic to form neutral atoms, let alone molecules. This raises a glaring paradox. How could the first molecular bonds emerge in an environment so hostile that it vaporized matter itself? The answer lies in a cosmic balancing act between fire and ice, where the universe's expansion acted as a giant thermostat, dialing down the temperature just enough for chemistry to flicker to life. Take hydrogen, the universe's simplest atom. For it to form a stable molecule, two hydrogen atoms need to approach each other slowly enough for their electrons to create a shared bond. But in the plasma phase, electrons were untethered and protons were like bumper cars in a nuclear reactor, constantly smashing apart before any meaningful handshake could occur. The tipping point came when the cosmos cooled below 3000 Kelvin, allowing electrons to finally latch onto protons and form neutral hydrogen. Yet even then, molecular bonds faced another hurdle. The leftover heat still made collisions too violent for atoms to stick together. Here's where the timeline gets controversial. Some models suggest molecules like helium hydride could have formed in isolated pockets where gas cooled faster, like eddies in a cosmic river. Others argue that the universe's expansion rate created a Goldilocks window, a brief period where temperatures dropped just enough for molecules to stabilize before radiation from the first stars reionized everything. The problem: observational evidence is maddeningly sparse. The Planck satellite's maps of the cosmic microwave background hint at temperature variations that might correlate with these early cooling zones. But teasing out molecular fingerprints from that ancient light is like trying to hear a whisper in a hurricane. Lab experiments add another layer of intrigue. By replicating primordial plasma in particle accelerators and laser-driven chambers, physicists have watched hydrogen molecules form in microseconds under conditions mimicking the early universe's fading heat. These studies reveal a startling truth. Molecules didn't need perfect calm to emerge, just a fleeting drop in the chaos. Like plants cracking through asphalt, the first chemical bonds seized every microscopic opportunity, exploiting brief dips in temperature or density to take root. Yet the debate rages on. Could some molecules have formed during the plasma phase itself, clinging to existence in shielded regions near dark matter clumps? A provocative theory suggests that quantum tunneling, where particles cheat energy barriers by jumping through them, might have allowed hydrogen pairs to bond even in hotter environments. If true, it would rewrite chemistry's origin story, proving that the universe's first molecules were even tougher and weirder than we imagined. The plasma phase paradox forces us to rethink the boundaries of chemistry. It's not just about elements and reactions, but about the universe's ability to carve order from chaos against impossible odds. And buried in that struggle might be the key to why anything more complex than hydrogen exists at all. Carbon shouldn't have existed in the early universe, at least, not in any significant amounts. Born from the fiery hearts of stars, this element requires 3 helium nuclei to fuse in a precise, high-energy dance called the triple alpha process. Yet somehow, traces of carbon appear in spectrographic readings of gas clouds so ancient they predate the first generation of stars. This cosmic anachronism has scientists scrambling to explain how stardust's most versatile building block could have slipped into the universe's chemical recipe book before the stars themselves were fully awake. One radical possibility lies in the brief but violent lives of population 3 stars, the hypothetical first generation of stellar giants. These behemoths, hundreds of times more massive than our Sun, burned furiously and died young, exploding as supernova within mere millions of years. Their deaths may have scattered carbon and other heavy elements like cosmic graffiti, tagging the primordial gas before more sedate stars could form. But here's where it gets speculative. Some models suggest these early supernovae could have produced carbon through exotic, high-energy pathways that bypass the usual stellar fusion chains. Imagine a star so massive its core becomes a particle accelerator, smashing nuclei together with enough force to forge carbon in single, chaotic bursts rather than the slow simmer of modern stars. Even stranger, carbon might have hitched a ride on the backs of primordial black holes. As these ancient gravitational monsters devoured surrounding gas, their accretion disks could have become temporary chemical factories, generating trace heavy elements in the maelstrom, elements later expelled in powerful jets. Telescopes have spotted carbon-rich clouds near modern black holes, hinting at this unexpected production line. If a similar process occurred in the early universe, it could explain carbon's premature debut. But carbon's early cameo isn't just a cosmic trivia fact, it reshapes our understanding of life's potential timeline. Deep in the cold reaches of interstellar space, carbon atoms teamed up with hydrogen and oxygen to form probiotic molecules like formaldehyde and hydrogen cyanide, long before planets or even proper stars existed. The Atacama Large Millimeter Array has detected these organic compounds in distant gas clouds dating back nearly 12 billion years, proving that the raw ingredients for life were cooking in the universe's kitchen far earlier than we'd assumed. Lab experiments revealed just how resourceful these early carbon compounds could be. Under conditions mimicking interstellar ice grains, simple carbon molecules spontaneously assemble into complex structures like polycyclic aromatic hydrocarbons, ringed compounds found in meteorites and comets. Some theories suggest these carbon skeletons might have acted as molecular scaffolds, helping larger organic molecules stabilize in the harsh radiation of deep space. The implications are staggering. If carbon was already weaving complex chemistry in the darkness, the universe might have been priming the pump for life billions of years before Earth formed. Every carbon atom in your DNA, every exhaled breath, every fossil fuel burned, all could trace their lineage back to these anomalous early appearances, forged in the chaos of stars that lived fast, died young, and left behind the seeds of everything we know. Oxygen is the third most abundant element in the universe today, essential for everything from the water in our bodies to the rust on distant asteroids. But in the universe's first chapters, oxygen was practically a ghost locked away in a cosmic vault with no key. Here's why: oxygen isn't forged in the Big Bang's initial fireball like hydrogen or helium. It's born in the hearts of stars, cooked up through nuclear fusion over millions of years, and in the early universe, those stars hadn't even formed yet. Without them, oxygen simply didn't exist in meaningful amounts, leaving the first molecules to assemble from a far more limited toolkit. This shortage created a stark divide between the universe's infancy and its modern era. Picture a vast desert where hydrogen and helium atoms drift like grains of sand. That was the primordial landscape. Compare it to today's molecular clouds like the Orion Nebula, where oxygen teams up with hydrogen to form water ice, clings to carbon in carbon monoxide, and weaves into complex organic molecules. Back then, none of that chemistry was possible. The earliest gas clouds weren't just oxygen poor, they were oxygen void, a reality that forced molecules to improvise with what little they had. Yet this absence might have been a blessing in disguise. Without oxygen's reactive presence, fragile molecules like helium hydride or lithium compounds got a rare chance to survive longer in the cooling cosmos. Modern experiments show that even trace amounts of oxygen can obliterate these primordial bonds, acting like a chemical bulldozer. In the early universe, their extended lifespans may have allowed them to shape gas dynamics in ways that later, oxygen-rich chemistry couldn't replicate. The real twist comes when we ask how oxygen eventually broke free. The first generation of stars, massive, short-lived giants, acted as cosmic alchemists, fusing helium into carbon and oxygen in their cores before exploding as supernova. These violent deaths scattered heavy elements like seeds across the void, but the process wasn't instant. Oxygen atoms spent their early existence trapped in stellar wreckage or locked in simple molecules like carbon monoxide, only gradually becoming available for more complex chemistry. Telescopes studying distant quasars have spotted this transition in action. Gas clouds from 12 billion years ago show oxygen levels 100 times lower than those in modern nebulae, a stark reminder of how late oxygen arrived to the party. What's fascinating is how this delay shaped the universe's chemical evolution. Without oxygen's interference, hydrogen molecules dominated long enough to cool the first gas clouds and trigger star formation. Later, when oxygen finally flooded the cosmos, it didn't just join the mix, it revolutionized it, enabling water, silicates, and eventually the chemistry of life. But those first molecules, they built the foundation in an oxygen-free world, proving that sometimes absence isn't just a limitation, it's a catalyst for cosmic creativity. Nitrogen plays a curious role in cosmic chemistry. It's everywhere in our modern universe, from the air we breathe to the proteins in our cells, yet it was virtually absent when the first molecules were forming. The reason nitrogen isn't a product of the Big Bang, unlike hydrogen or helium, which spilled forth from the universe's explosive birth, nitrogen had to wait for the fiery furnaces of stars to assemble it, one proton at a time. This delay meant that while hydrogen molecules were busy shaping the early cosmos, nitrogen was still trapped in stellar cores, waiting for its chance to join the chemical dance. The bottleneck wasn't just about production, it was about survival. Even when nitrogen finally escaped into space through supernova or stellar winds, it faced brutal conditions. Ultraviolet radiation from young stars could easily rip nitrogen atoms apart or ionize them into unreactive states. For nitrogen to become part of molecules, it needed a cosmic safe haven somewhere cool and shielded, like the icy surfaces of dust grains or the dense hearts of molecular clouds. That's where ammonia finally made its debut. This simple compound, just one nitrogen atom bonded to 3 hydrogens, might seem unremarkable, but it became a game-changer for astrochemistry. Ammonia's stability made it a nitrogen reservoir, protecting the precious element from destruction while offering a springboard for more complex chemistry. Lab experiments show that when ammonia forms on interstellar ice grains, it can react with carbon compounds to form precursors for amino acids, the building blocks of life. In the frigid depths of space, these reactions might have been slow, but over millions of years, they could have stockpiled the ingredients for biology long before planets formed. The Rosetta mission's discovery of ammonia-rich ices on Comet 67P underscores nitrogen's cosmic journey. These frozen relics, preserved since the solar system's birth, suggest ammonia was already woven into the fabric of planetary nurseries. Even more intriguing are the nitrogen-rich organic molecules found in meteorites like Murchison, which hint at a hidden pipeline between stellar factories and life's raw materials. Yet nitrogen's scarcity in the early universe raises a provocative question. Did life's chemistry have to wait for stars to churn out enough nitrogen, or were there overlooked pathways that allowed nitrogen compounds to form earlier? Recent models suggest that in the turbulent environments around supernova, shock waves might have forced nitrogen into simple molecules even before the cosmos cooled. If true, nitrogen's story isn't just about rarity, it's about resilience, finding a way to matter even when the universe seemed stacked against it. Sulfur isn't usually the first element that comes to mind when we picture the universe's earliest chemistry. Hydrogen and helium steal the spotlight, while carbon and oxygen dominate later chapters. But sulfur might be the cosmic wildcard we've underestimated. Astronomers have spotted its spectral fingerprints in gas clouds surrounding quasars so distant their light has traveled over 12 billion years to reach us. That means sulfur was already woven into the fabric of the cosmos when the universe was less than a tenth of its current age, long before many heavier elements existed in significant quantities. How did sulfur get there so early? The prevailing theory points to the deaths of massive population, 3 stars, those first-generation giants that lived fast and died violently. When these stars exploded as supernova, their cataclysmic deaths forged sulfur in their cores and blasted it into space alongside other heavy elements. But here's the puzzle: sulfur is notoriously reactive. In the harsh ultraviolet glare of the early universe, it should have bonded almost instantly with hydrogen or metals, vanishing into molecules like hydrogen sulfide or sulfur monoxide. Yet quasar observations reveal something unexpected: free sulfur atoms lingering in ancient gas clouds, as if something shielded them from their own destructive tendencies. One explanation hinges on cosmic dust. Microscopic silicate grains could have acted as sulfur's bodyguards, providing surfaces where sulfur atoms adhered safely, avoiding destructive radiation. Lab experiments support this. When sulfur condenses onto simulated stardust in vacuum chambers, it forms stable coatings that resist ionization. Another possibility is even stranger. Some models suggest sulfur might have hitchhiked on molecular ions like H3+, forming temporary alliances that protected it long enough to influence surrounding chemistry. Imagine sulfur atoms clinging to these interstellar taxis, riding them through hostile environments until conditions were right to jump ship and form new bonds. But the real controversy isn't just how sulfur survived, it's what it did next. In modern nebulae, sulfur plays a key role in cooling gas clouds, helping them collapse into stars. Did it serve the same function in the primordial universe, detecting sulfur hydride? A simple molecule of sulfur and hydrogen in ancient gas could answer that. The problem: its spectral lines are faint and easily drowned out by background noise. Radio telescopes like a LM are now scanning for these whispers, hunting for proof that sulfur didn't just exist early but actively shaped the cosmos. Sulfur's early presence forces us to rethink the timeline of cosmic chemistry. If it was already enriching gas clouds when the first galaxies were forming, it might have accelerated star birth, seeding the universe with heavy elements faster than we thought possible. Or perhaps it was a bystander, a trace element with outsized curiosity value. Either way, sulfur's story reminds us that the universe's first molecules weren't just about hydrogen and helium. Sometimes, the unlikeliest players leave the deepest footprints. Phosphorus is the quiet oddball of cosmic chemistry, an element so rare in the early universe that finding it should have been like spotting a single grain of sand on an endless beach. Yet without it, life as we know it wouldn't exist. This underdog element is the backbone of DNA, the energy currency of cells, and the scaffolding of bones. So how did something so scarce become so vital? The answer lies in a cosmic game of hide and seek, where phosphorus's elusive nature might hold clues to one of astronomy's biggest mysteries, the Fermi paradox. In the pristine gas of the early cosmos, phosphorus was virtually non-existent. Unlike hydrogen or helium, it wasn't forged in the Big Bang. Unlike carbon or oxygen, it couldn't be cooked up in ordinary stars. Phosphorus required a specific, violent birth, a supernova explosion so powerful it could fuse silicon nuclei into phosphorus atoms, then blast them into space. Even then, these newborn phosphorus atoms faced near-instant peril. Reacting eagerly with oxygen to form phosphates or binding with iron into brittle minerals, most phosphorus ended up locked away in rocks or dust, vanishing from the gas phase where it could participate in chemistry. This scarcity creates a staggering bottleneck. Modern Earth's biology relies on phosphorus, but if early planets orbited stars born from phosphorus-poor gas clouds, they might have lacked enough to spark life. Astronomers call this the phosphorus problem, and it's not just theoretical. Studies of the Crab Nebula, a supernova remnant, reveal phosphorus levels 10 times lower than predicted, while surveys of ancient stars show wild fluctuations in this element's abundance. Some systems got lucky, others starved. Here's where the Fermi paradox creeps in. If life requires phosphorus and phosphorus is unevenly distributed, could entire regions of the galaxy be barren simply because this one element didn't show up in time? The implications are haunting. We might not see alien civilizations not because they don't exist, but because their chemistry never got off the starting block. Yet phosphorus's story isn't just about absence, it's about survival. Recent discoveries suggest this element had a cosmic Houdini act. Meteorites like the famed Murchison specimen contain phosphorus bound in exotic minerals like schrebersite, which react with water to release phosphides, a form more accessible to prebiotic chemistry. In the freezing voids of space, phosphorus might have hitched rides on comets or ice-coated dust grains, sheltered from destructive radiation until it reached newborn planets. Lab experiments add another twist. When subjected to simulated interstellar conditions, phosphorus compounds can form surprising molecules like phosphine, a gas recently detected in Venus's atmosphere, or even link up with carbon to create phosphorus-bearing organics. These pathways hint that the universe, despite its stinginess with phosphorus, found workarounds to sneak it into life's recipe. So is phosphorus the universe's rarest essential ingredient, or just its most resourceful? The answer might determine whether we're cosmic miracles or just the lucky winners of a galactic lottery. Carbon gets all the glory when we talk about life's building blocks, but what if the universe flirted with silicon first? This brittle, metallic element sits right below carbon on the periodic table, sharing its knack for forming 4 bonds. Yet we rarely consider its potential role in the cosmos's earliest chemistry. Here's why that might be a blind spot. In the scorching temperatures of the early universe, silicon had one critical advantage over carbon. It could bond with oxygen at much higher energies, forming tough silicate molecules long before carbon had a chance to stabilize. Picture grains of sand surviving a furnace where sugar would vaporize that silicon's endurance in the primordial chaos. While carbon needed the relative calm of stellar nurseries to assemble into complex organics, silicon was already busy shaping the cosmos in subtler ways. Microscopic silicate dust grains, forged in the explosions of ancient stars, became the universe's first solid surfaces. These flecks, no larger than a wavelength of light, offered something revolutionary, a stage where atoms could meet and react outside the gas phase. Laboratory experiments show that silicate surfaces act like cosmic Velcro, trapping hydrogen and carbon monoxide to form methanol and even formaldehyde molecules we normally associate with carbon chemistry. The twist: these reactions might have happened before carbon-rich environments existed, making silicon the silent architect of probiotic chemistry, but the plot thickens. Some astrobiologists speculate that if silicon-based molecules had more time to evolve, they could have sparked alternative biochemistries. On Earth, life chose carbon for its versatility, but in hotter, more acidic environments like volcanic vents or exoplanet atmospheres, silicon's stability might have been the better gamble. Imagine microbial life forms with crystalline skeletons, metabolizing sulfur instead of oxygen, their biochemistry built on silicate chains rather than carbon backbones. While purely hypothetical, these scenarios aren't science fiction, they're testable. NASA Ames Research Center has synthesized silicon-based analogs to DNA in simulated planetary conditions, proving that the elements can form complex, self-replicating structures under the right circumstances. The real controversy lies in the cosmic timeline. Did silicon's early chemistry pave the way for carbon, or were they competitors? Radio telescopes have detected silicon monoxide in protostellar disks, a molecule that could have seeded planet-building material. Meanwhile, meteorites like Alend contain silicon carbide grains older than the Sun, hinting at silicon's deep-rooted role in planetary ingredient lists. Yet for all its early advantages, silicon faced a cosmic glass ceiling. While it excelled at forming hardy minerals and crystals, it struggled with the dynamic, reversible bonds that make carbon so versatile for life. A silicon-based protein, for example, would be too rigid to fold and unfold like its carbon counterpart, a limitation that might have sealed its fate once cooler, water-rich environments took over. So why does this matter now? Because every rocky planet, Earth included, is built on a foundation of silicate chemistry. The mountains beneath our feet, the glass in our windows, even the magma churning in Earth's core all trace back to silicon's early cosmic handiwork. By downplaying its role, we might be missing a key chapter in how chemistry transitioned from simplicity to complexity. The next time you hold a piece of quartz, remember, you're touching a relic from an era when silicon ruled the molecular world, and in some corners of the universe perhaps it still does. Magnetic fields might seem like background players in the drama of cosmic chemistry, an invisible force we associate with compass needles or sunspots rather than molecule formation. But what if these silent ripples in space actually orchestrated the universe's first chemical bonds? Picture the early cosmos not as a formless void, but as a tapestry of delicate magnetic threads, weaving through gas clouds and subtly nudging atoms into place. Under their influence, chaotic particle collisions could have transformed into orderly molecular handshakes, turning randomness into structure. Modern astronomy offers clues to this hidden role. In star-forming regions like the Orion Molecular Cloud, telescopes detect magnetic fields aligning dust grains like microscopic compasses. These grains, in turn, act as scaffolds for molecule formation, their surfaces providing sheltered meeting spots where hydrogen and carbon monoxide can bond without being torn apart by radiation. Lab experiments back this up. When scientists simulate interstellar conditions with magnetic fields, molecules form faster and more efficiently, as if the fields are guiding atoms into the right configurations. But the early universe's magnetic fields weren't just faint whispers, they might have been cosmic conductors. Theories suggest that in the first billion years, turbulent plasma motions could have amplified weak primordial fields, creating vast magnetic highways that channeled gas flows. These channels would have concentrated matter into dense filaments, creating pressure cookers where molecules like hydrogen, deuteride, or even water ice could assemble. Without this scaffolding, gas might have remained too diffuse for chemistry to gain a foothold. The smoking gun, ancient quasars, their light passing through billion-year-old gas clouds, carries subtle polarization signatures, hints that magnetic fields were already shaping molecular chemistry when the universe was a fraction of its current age. Even more compelling are observations of protostellar disks, where magnetic fields twist and braid like DNA, funneling material onto growing stars while leaving behind molecular-rich outskirts. It's a pattern that echoes across scales, from galaxy clusters to the birthplaces of planets. Yet not all fields were helpful. Some simulations show overly strong magnetism can stifle molecule formation by preventing gas clouds from collapsing entirely. This delicate balance between guidance and obstruction might explain why certain regions of the early universe became molecular factories while others remained barren. The difference could have come down to the strength and geometry of fields we're only now learning to measure. If magnetic fields truly were the invisible hands shaping our chemical origins, it redefines how we see the cosmos's blueprint. No longer just a sea of particles, but a dynamic arena where forces we can't even see choreograph the steps toward complexity. And somewhere in that ancient dance, the universe learned how to build not just molecules, but the foundations for everything that followed. The universe's baby picture, the cosmic microwave background, is more than just a snapshot of the Big Bang's afterglow. Embedded in its faint, mottled patterns could be the ultimate clue to how and when the first molecules emerged. These temperature fluctuations, frozen in time for 13.8 billion years, aren't just random noise. They're cosmic breadcrumbs leading us back to the moment chemistry began. Imagine sunlight filtering through a forest canopy, leaving patches of warmth and shadow on the ground. The CMB does the same thing, but instead of leaves, its shadows were cast by the earliest structures in existence, regions where matter was just dense enough for molecules to take root. What makes this map so revolutionary is its precision. Satellite missions like Planck have measured these temperature variations down to millionths of a degree, revealing a universe that was subtly lumpy from the start. Those tiny hot and cold spots weren't arbitrary. They marked the gravitational seeds of everything to come. And here's where molecules enter the story. As hydrogen and helium atoms began pairing up, they subtly altered how the CMB's light traveled through space. Molecular hydrogen, for instance, absorbs and re-emits radiation at specific wavelengths, leaving a faint but detectable fingerprint in the CMB's polarization patterns. It's like finding fossilized raindrop impressions in ancient mud. The molecules themselves are long gone, but their ghostly imprint remains. The real breakthrough came when scientists realized these fluctuations weren't just relics. They were active participants in the universe's chemical evolution. Denser regions where matter clumped slightly more, cooled faster thanks to molecular hydrogen's ability to radiate heat away. This created a feedback loop. As gas cooled, molecules formed more easily, which further accelerated cooling, eventually triggering the collapse of the first protogalaxies. The CMB's cold spots might literally be the birthmarks of chemistry's first triumphs, but the plot thickens when we consider helium hydride. This fragile molecule, if present in the early universe, would have left a distinct signature in the CMB's spectral distortions, a bump at specific frequencies where its bonds vibrate. While we haven't detected it yet, upcoming missions like the proposed Primordial Inflation Explorer aim to scour these ancient light patterns for traces of helium hydride's fleeting existence. Finding it would be like discovering a single brushstroke in a painting, confirming that molecule formation began even before the cosmic dark ages ended. Of course, not all CMB fluctuations point to molecules. Some reflect primordial sound waves echoing through the plasma, while others hint at dark matter's gravitational tug. The challenge is untangling these signals, a task that's pushed astrophysicists to develop algorithms capable of isolating chemistry's subtle whispers from the cosmic chorus. Recent studies suggest that certain asymmetries in the CMB's polarization could be the smoking gun for early molecular activity, particularly if they align with predictions from quantum chemistry models. What's staggering is how much we can infer from these faint temperature differences. By comparing CMB maps with simulations of molecular formation, researchers have estimated that the universe's first chemical bonds likely appeared when it was just a few 100 million years old, a blink in cosmic terms. And if future telescopes can pinpoint the exact moment hydrogen molecules began dominating over atomic hydrogen, we'll have a definitive timestamp for chemistry's Big Bang. The CMB isn't just a relic, it's a time machine. Every new analysis peels back another layer, revealing how the universe's slightest imperfections grew into the rich molecular tapestry we see today. And somewhere in those ancient ripples, the first bonds are still telling their story, if only we know how to listen. Neutrinos are the universe's most elusive particles, so ghostly they pass through light years of lead without a single collision. Yet these nearly massless, chargeless specters might have played a surprising role in the birth of the first molecules. Here's the twist: while we think of chemistry as the domain of electrons and electromagnetic forces, the early universe was so dense and hot that even the feeble, weak nuclear force mediated by particles like neutrinos could have orchestrated molecular handshakes. Picture a cosmic dance where molecules formed not through the usual electron exchanges, but through ephemeral neutrino interactions, fleeting as whispers in a storm. This hypothesis hinges on the peculiar nature of weak force reactions, visualized in Feynman diagrams as intricate subatomic waltzes. Normally, neutrinos barely interact with matter. Trillions pass through your body every second without a trace. But in the searing plasma of the primordial universe, conditions were anything but normal. With particles packed shoulder to shoulder and temperatures exceeding 10 billion degrees, neutrinos could have acted as matchmakers, briefly enabling protons and neutrons to swap identities through beta decay. These swaps, though momentary, might have allowed exotic molecular hybrids to flicker into existence, unstable pairings of particles that shouldn't last, but did just long enough to alter the chemistry of the early cosmos. Lab experiments hint at the plausibility of this idea. When physicists slam neutrinos into heavy water targets in detectors like supercamioc, and they occasionally trigger nuclear transformations, proving these particles can indeed meddle in atomic affairs. Extrapolate that back to the universe's first minutes, and the math suggests neutrino-induced reactions could have produced deuterium or even helium hydride at rates far higher than traditional models predict. The catch: these neutrino-built molecules would have been bizarrely fragile, collapsing almost instantly unless they found shelter in the quantum chaos. Some theories propose that in the turbulence of the early plasma, density fluctuations created temporary safe zones where these exotic bonds could persist microseconds longer, enough to influence surrounding gas dynamics. The real smoking gun might lie in the cosmic neutrino background, the faint relic glow of neutrinos from the Big Bang, analogous to the cosmic microwave background but far harder to detect. If future observatories like Ptolemy could capture its spectral distortions, they might find imprints of these early weak force molecules etched like shadows in the neutrino fog. Until then, the idea remains a tantalizing what if, a reminder that the universe's first chemistry might have been stranger than anything we've dared to simulate. So next time you hear that neutrinos are nearly invisible, remember, in the right conditions, even ghosts can build. Gravity might seem like the brute force of the cosmos, crushing stars into black holes and warping the fabric of space-time, but in the delicate dance of molecule formation, it played the role of a meticulous sculptor. Without the subtle clumping of matter in the early universe, those first fragile bonds between atoms might never have stabilized. Here's why. In a perfectly smooth cosmos, hydrogen and helium atoms would have drifted too far apart, their collisions too rare and feeble to forge lasting connections. But gravity's fingerprints were already etched into the universe's infancy, creating minute density variations that became the cradle for chemistry itself. These cosmic wrinkles didn't emerge by chance. Quantum fluctuations in the instant after the Big Bang stretched across the expanding universe, leaving some regions slightly denser than others. Over millions of years, gravity amplified these differences, pulling matter into faint webs and filaments. Within these denser pockets, gas particles crowded closer together, colliding more frequently, and with just enough pressure to overcome their natural repulsion. Picture a crowded subway car where passengers are forced shoulder to shoulder. Suddenly, even the most reserved strangers might strike up a conversation. That's what happened with atoms. In the denser regions, hydrogen pairs found the proximity they needed to whisper their first molecular secrets. Simulations of this epoch reveal how crucial these gravitational instabilities were. Run the clock backward in a virtual universe with perfectly even matter distribution, and molecules form sluggishly, if at all. But introduce even a 1% density fluctuation, and the chemistry accelerates dramatically. Gas clouds in these models don't just cool, they fragment, with molecular hydrogen acting like a cosmic refrigerant, radiating heat away and allowing gravity to further compress the gas. It's a feedback loop that turns faint ripples in the primordial plasma into stellar nurseries. The real magic lies in the timing. Too soon, and the universe's residual heat would have torn molecules apart before they could stabilize. Too late, and the first star's ultraviolet radiation would have reionized the gas, resetting the chemical clock. Gravitational collapse had to strike during a narrow window, a Goldilocks era when temperatures were just low enough for molecules to form but high enough to keep atomic motions energetic. Remarkably, the universe's expansion rate and matter content lined up this window perfectly, as if fine-tuned for chemistry's debut. Yet gravity's role wasn't uniform. Some regions collapsed faster, their density spikes creating localized pressure cookers where exotic molecules like lithium hydride could briefly flourish. Others languished in near vacuums, their atoms too isolated to bond. This patchwork might explain why modern telescopes detect uneven distributions of ancient molecules. Some corners of the cosmos were simply luckier in the gravitational lottery. Future experiments aim to test this theory by probing the cosmic microwave background for telltale distortions caused by early molecular cooling. If certain polarization patterns align with predictions from gravitational collapse models, it would be like finding the universe's original recipe written not in atoms or light, but in the silent pull of gravity's hand. From quantum seeds to celestial structures, gravity's quiet choreography reminds us that the universe's grandest chemistry didn't just depend on elements and reactions. It needed a stage, and gravity built it one invisible thread at a time. Supersymmetry isn't just a fringe theory, it's a radical reimagining of reality that could rewrite the entire timeline of cosmic chemistry. At its heart lies a bold idea. Every known particle has a hidden twin, a superpartner lurking just beyond our current detection. These hypothetical particles, dubbed squarks, photinos, and sleptons, aren't just exotic trivia. They might have been the universe's original molecular architects, sculpting bonds in ways the standard model can't explain. Picture the early cosmos not as a sparse soup of familiar particles, but as a bustling quantum metropolis where these shadowy twins outnumbered ordinary matter 1,000 to 1. Under those conditions, chemistry wouldn't have followed the rules we know. It would have operated on an entirely different playbook. Here's where it gets mind-bending. Supersymmetric particles are thought to interact via forces we've yet to fully describe, some mediated by gravitinos or other exotic carriers. In the searing heat of the early universe, these interactions could have forged transient, supermolecules, structures where particles and their superpartners briefly paired up before decaying. Labs like CERN have hunted for traces of these phenomena by smashing protons together at near-light speeds, hoping to catch a glimpse of supersymmetry's fingerprints in the debris. While no definitive proof has emerged, certain anomalies in collision data like unexpected energy imbalances hint that we might be brushing against something monumental. The implications for molecular origins are staggering. If superparticles existed even fleetingly, their sheer abundance would have dramatically accelerated early chemistry. Hydrogen molecules might have formed not through slow, probabilistic collisions, but through mediated interactions where supersymmetric particles acted as cosmic matchmakers. Some models suggest these processes could have jump-started molecular cooling hundreds of millions of years earlier than traditional theories allow, telescoping the timeline of star formation. Telescopes peering at ultra-distant quasars have spotted puzzlingly mature galaxies where none should exist. Could supersymmetry's hidden hand explain their premature brilliance? Yet the most tantalizing clues might lie in the cosmic microwave background. Supersymmetric interactions would have subtly altered how light polarized in the early universe, leaving faint but detectable imprints in the CMB's swirling patterns. Projects like the Simons Observatory are now scouring these ancient light maps for deviations that could point to physics beyond the standard model. A confirmed signal wouldn't just validate supersymmetry, it would upend our understanding of when and how molecules first stitched the cosmos together. Critics argue this is all speculative grandeur, that inventing unseen particles to solve cosmic riddles is like adding epicycles to planetary orbits. but supporters counter that nature has repeatedly shown us reality is stranger than our theories. After all, neutrinos were once dismissed as mathematical ghosts until detectors proved otherwise. Whether supersymmetry's molecular revolution holds up or not, it forces us to confront a humbling truth. The universe's first chemistry might have been orchestrated by players we've yet to meet. Black holes are often seen as the ultimate destroyers, cosmic vacuum cleaners that devour everything in their path, even light itself. But what if, in the universe's earliest moments, these gravitational monsters played an unexpected role as molecular midwives? The idea hinges on a paradox. The very radiation that should tear molecules apart might have also created the perfect conditions for them to form. Primordial black holes, hypothetical relics from the Big Bang, smaller than an atom yet denser than a star, could have been the key. Unlike their modern counterparts, these tiny titans wouldn't have lurked silently in space. Thanks to Hawking radiation, they would have fizzled with energy, emitting particles and heat as they slowly evaporated. Conventional wisdom says this radiation is destructive, blasting apart any nearby atoms before they could bond. Yet in the strange physics of the early cosmos, destruction and creation often walked hand in hand. Picture a swarm of these micro-black holes, each one a flickering beacon in the darkness. Their Hawking radiation wouldn't have been uniform. It would have pulsed in unpredictable bursts, creating zones of intense heat right beside regions of relative calm. In those fluctuating environments, hydrogen atoms might have been ionized one moment, stripped of their electrons, only to recapture them microseconds later as the radiation faded. These rapid cycles of destruction and recombination could have acted like a cosmic forge, hammering atoms into molecules through sheer persistence. Lab experiments with plasma physics hint at this possibility. When subjected to pulses of extreme energy, ionized gases sometimes reorganize into molecular structures faster than expected, as if chaos itself catalyzes order. The real twist comes when we consider temperature. Hawking radiation from small black holes is incredibly hot, millions of degrees, but its reach is limited. Just outside the kill zone, the surrounding gas could have cooled rapidly, creating steep thermal gradients. These gradients are like molecular assembly lines. Atoms get a kick of energy near the black hole, then drift outward to cooler regions where they can stabilize into bonds. It's a process eerily similar to how modern chemists use temperature variations to synthesize compounds in labs, just scaled up to cosmic proportions. But there's a catch. For every molecule forged, countless others would have been obliterated. This balance between creation and destruction might explain why some regions of the early universe became molecular nurseries while others remained barren. Computer simulations of primordial black hole swarms show patchy molecular distributions, with dense knots of hydrogen and helium hydride surrounded by vast, empty voids. That matches observations of ancient gas clouds, where molecule-rich areas appear oddly clustered, as if shaped by invisible, localized energy sources. The most tantalizing clue lies in the cosmic infrared background, a faint glow permeating the universe. Some theorists argue that primordial black holes' collective evaporation could have left subtle fingerprints in this radiation-specific wavelengths where their fleeting existence briefly warmed the cosmos. Future telescopes like the SPHEREX mission might detect these whispers, revealing whether these tiny black holes were indeed the universe's unlikeliest chemists. So were black holes destroyers or creators? The answer might be both. In their violent flickering, they could have carved out the niches where chemistry first took hold, proving that even the darkest forces in the universe have a hidden knack for building. What if the first molecules in our universe weren't homegrown at all but cosmic stowaways, smuggled in from other realities? The idea sounds like science fiction, but some physicists take it seriously. Imagine a frothing sea of multiverses, each with its own laws of physics, occasionally brushing against one another like soap bubbles in a sink. In those fleeting moments of contact, could particles, or even entire molecules, have tunneled through the barriers between worlds, seeding our universe with chemistry that wasn't supposed to exist here? This wild possibility hinges on quantum tunneling, a phenomenon where particles cheat physics by teleporting through barriers they classically shouldn't overcome. In labs, we see electrons pull this trick all the time, vanishing from one side of an impenetrable wall and reappearing on the other. Scale that up to cosmic proportions, and you get a startling proposal. During the universe's inflationary period, when space-time stretched faster than light, quantum fluctuations might have punched microscopic wormholes between neighboring universes. Through these fleeting tunnels, exotic molecules from alternate realities could have slipped into our cosmos, bringing with them chemical blueprints our own laws hadn't yet invented. The smoking gun might lie in anomalies, molecules that defy expectations. Take helium hydride, detected in modern nebulae but mysteriously absent from ancient gas clouds where it should have thrived. Could its patchy distribution hint at an extraterrestrial origin, a molecule more at home in a universe with slightly different binding energies? Even stranger are theoretical compounds like Strangelet's quark clusters, stable only under extreme conditions. If these slipped through from a high-energy universe, they might have catalyzed reactions impossible in our native physics, acting as molecular seeds for structures we're only beginning to understand. Critics argue this is speculative overreach, but supporters point to the cosmic microwave background's cold spot, a vast, anomalously chilly region in space that some interpret as a bruise from a long-ago collision with another universe. If such impacts occurred, they wouldn't just leave thermal fingerprints. They could have sprayed foreign matter across our infant cosmos like paint from a burst balloon. Future telescopes hunting for primordial gravitational waves might find corroborating evidence, ripples in space-time carrying the echoes of these multiverse crashes. The most mind-bending twist: contamination could run both ways. If molecules leaked into our universe, others might have leaked out, meaning our cosmos could have unknowingly exported its chemistry to stranger realms. Somewhere in the multiverse's infinite tapestry, there might be a reality where helium hydride is as common as water, all because our newborn universe once brushed against theirs in the dark. Whether proof or pipe dream, the multiverse contamination theory forces us to ask a humbling question: how much of our cosmic history was borrowed and how much was truly ours? Time crystals sound like something ripped from a science fiction novel. Structures that repeat not just in space but in time, their atoms oscillating in an eternal loop without energy input. Yet these exotic phases of matter, first theorized in 2012 and later created in labs, might hold the key to one of cosmology's strangest puzzles: how the earliest molecules organized themselves in a universe that hadn't yet settled into stable rhythms. Imagine a molecular waltz where the dancers move in perfect, self-sustaining sequences, their bonds pulsing like metronomes set by the fabric of space-time itself. In the chaos of the early cosmos, traditional chemistry faced a brutal obstacle: temperatures so extreme that most bonds shattered instantly, but time crystals operate differently. Their secret lies in broken time symmetry, a phenomenon where their atomic arrangements repeat at fixed intervals, immune to the disarray around them. Lab experiments with trapped ions or nitrogen vacancy diamonds have shown this isn't just theory. Under precise conditions, these systems lock into rhythmic patterns that resist entropy. Scale this up to the post-Big Bang universe, and you get a provocative idea. What if the first hydrogen or helium hydride molecules didn't just form randomly, but crystallized along invisible temporal scaffolds? Here's how it might have worked. As the universe cooled, quantum fluctuations could have birthed microscopic time crystal domains, patches where matter's vibrations synchronized like pendulum clocks on a shared wall. Within these zones, atoms wouldn't just collide, they'd resonate, their interactions amplified by collective rhythm. Hydrogen pairs, for example, might have stabilized not through slow, probabilistic encounters, but by slotting into these pulsating lattices like gears in a cosmic clock. The implications are staggering. Instead of relying on chance, molecular formation could have been orchestrated by an underlying temporal architecture, turning randomness into order. Evidence for this is still circumstantial but tantalizing. Modern time crystals exhibit eerily familiar behaviors, self-correcting oscillations that mimic the fault tolerance seen in protein folding or DNA replication. Some theorists suggest this isn't coincidence, but a thermodynamic echo of the universe's first self-organizing principles. Even more compelling are anomalies in the cosmic microwave background, where certain polarization patterns align too neatly to be random, as if etched by recurring quantum vibrations. Yet critics argue time crystals are too delicate to have survived the early universe's violence. Today's lab-made versions require near absolute zero temperatures and pristine isolation conditions utterly unlike the seething plasma of the cosmos's infancy. But proponents counter that the rules change when quantum gravity enters the picture. In the first microseconds, space-time itself might have been granular, its foamy texture providing the perfect substrate for temporal order to take root. Picture a surfer riding a wave. The turbulence beneath doesn't disrupt their balance, it enables it. Whether time crystals shaped our molecular origins or not, their very existence forces us to rethink chemistry's boundaries. Perhaps the universe didn't just stumble into complexity, it pulsed, resonated, and danced its way there, one tick of the cosmic clock at a time. What if the molecules we see around us, the ones that form stars, planets, even our own bodies, aren't truly three-dimensional objects, but ghostly projections of information encoded on a distant, two-dimensional surface? This isn't science fiction, it's the holographic principle, a radical idea born from black hole physics and string theory that could rewrite how we understand the origins of chemistry itself. The theory hinges on a bizarre property of black holes. When matter falls into one, it doesn't just vanish, it leaves an imprint on the event horizon, the point of no return. Like a cosmic fingerprint, this information gets etched onto the black hole's surface in tiny, Planck-scale pixels. The holographic principle takes this further, proposing that the entire universe might operate the same way, that the three-dimensional reality we experience is just a projection of information stored on a distant, two-dimensional boundary. Now imagine applying this to the first molecules. Under the holographic lens, hydrogen pairs or helium hydride wouldn't be independent objects floating in space. They'd be shadows cast by quantum interactions happening on the universe's edges. This flips chemistry on its head. Molecular bonds wouldn't form because atoms attract each other in 3D space, but because they're underlying 2D data entangled in specific ways. It's like watching a movie and realizing the characters aren't real, just patterns of light projected from a flat screen. String theory gives this idea legs through something called AD/CFT correspondence, which mathematically links a higher dimensional space like our universe to a lower dimensional shadow world where physics plays by different rules. In this framework, the vibrational patterns of strings in the 2D boundary could manifest as molecular forces in our 3D world, the energy holding a hydrogen molecule together. Just a holographic echo of string interactions we can't directly see. There's tantalizing, if indirect, evidence for this. Quantum entanglement, a phenomenon where particles influence each other instantly across vast distances, behaves suspiciously like a holographic projection, as if their connection exists outside ordinary space. Lab experiments with ultra-cold atoms have even simulated holographic dynamics, showing how 3D behaviors can emerge from 2D systems. The implications for cosmic chemistry are staggering. If molecules are projections, their formation in the early universe might have depended less on temperature or density, and more on how information pooled and interacted on this primordial surface. It could explain why certain molecular distributions in ancient gas clouds appear oddly correlated over impossible distances, like shadows cast by a single unseen light. Critics argue this is speculative overreach with too few testable predictions, but supporters point to anomalies in the cosmic microwave background, subtle correlations that align with holographic models. Future quantum gravity experiments might settle the debate, probing whether reality truly has a hidden layer where chemistry's first strokes were drawn. Whether the holographic principle holds up or not, it forces us to ask, what are molecules really? If even the simplest bonds are glimpses of a deeper code, then the universe's first chemistry wasn't just about atoms, it was about information learning how to dance. Quantum entanglement isn't just a bizarre quirk of physics. It might have been the invisible hand that stitched together the universe's first molecules. Picture this: two particles become entangled, their fates intertwined across any distance, so that changing one instantly affects the other. Now imagine that same spooky connection, not just linking particles, but actively forging chemical bonds between atoms in the early cosmos. This isn't science fiction, it's a radical theory that rewrites the rules of chemistry from the ground up. Think of entanglement as the ultimate cosmic shortcut. Normally, atoms form bonds by sharing or exchanging electrons, a process governed by electromagnetic forces. But in the seething chaos of the early universe, where temperatures were too extreme for stable electron clouds, entanglement could have bypassed traditional chemistry entirely. Instead of relying on slow, probabilistic collisions, atoms might have felt each other's presence through quantum links, snapping together like magnets even before their electron shells overlapped. It's as if the universe didn't wait for chemistry, it cheated, using entanglement to pre-wire bonds before the ingredients were fully ready. Lab experiments with qubits, the quantum equivalent of bits, hint at how this could work. When entangled, qubits can perform calculations in parallel, as if connected by an invisible thread. Apply that to molecular formation, and you get a scenario where hydrogen atoms don't just randomly collide, they're drawn together by quantum correlations imprinted in the fabric of spacetime itself. Some physicists even speculate that these protobonds could have been fractal, with entangled networks of atoms forming intricate, self-similar patterns like cosmic snowflakes. The smoking gun might lie in the cosmic microwave background. If entanglement drove early molecular formation, its fingerprints could linger in the polarization patterns of ancient light, subtle swirls betraying where quantum connections once shaped matter. Telescopes like the Simons Observatory are already hunting for these anomalies, and if found, they'd prove that chemistry's roots aren't just electromagnetic. They're quantum, woven into the universe's blueprint from the very first moments. Critics argue entanglement is too fragile to survive the early universe's turbulence, but supporters counter with a bold idea. What if the cosmos was born entangled? In the infinitesimal instant after the Big Bang, every particle could have been quantum linked, creating a vast, interconnected web where chemistry unfolded not atom by atom, but as a synchronized cosmic dance. If true, it means every molecule in existence, from the water in your cells to the oxygen in your lungs, might trace its lineage back to a quantum handshake written into the laws of reality itself. This isn't just a new way to build molecules, it's a new way to see the universe. If entanglement shaped the first bonds, then chemistry isn't just about atoms and forces. It's about information, connection, and the hidden threads that tie everything together. And somewhere in those threads, the universe's oldest secrets might still be waiting to unravel. Dark matter doesn't interact with light or ordinary matter, or so we thought. Hidden in the shadows of the cosmos, a hypothetical particle called the action might have played puppeteer to the universe's first molecules. These ghostly particles, theorized to solve a quantum puzzle in particle physics, could have been the unseen midwives of cosmic chemistry, coaxing atoms together when the universe was too hot and chaotic for traditional bonds to survive. Actions are bizarre even by dark matter standards. Unlike WIMP or other candidates, they're ultra-lightweight, potentially billions of times lighter than electrons, and they behave less like particles and more like waves, oscillating through space with a rhythm tuned to the universe's expansion. This wave-like nature gives them a peculiar superpower. They can subtly influence electromagnetic fields. In the early universe, that could have meant creating faint, fluctuating force fields that guided hydrogen or helium atoms into alignment, like cosmic traffic cops directing particles into molecular parking spots. The math is tantalizing. Quantum calculations show that action waves passing through primordial gas clouds would have generated oscillating electric dipoles, tiny, shifting charges on atoms that made them more likely to stick together. It's like rubbing a balloon on your hair to create static cling, except the rubbing was done by invisible dark matter rippling through space. These dipole moments might have been fleeting, but in the dense plasma of the early cosmos, even microseconds of extra attraction could have tipped the scales toward molecule formation. Lab experiments are now racing to test this idea. At the University of Washington's Action Dark Matter experiment, scientists use supercooled magnets to hunt for actions converting into microwave photons. While their goal is detecting dark matter, the same setup could reveal how action fields interact with hydrogen, data that might confirm their role in early chemistry. Meanwhile, quantum simulators at CERN are recreating primordial conditions with ultracold rubidium atoms, watching how hypothetical action-like fields alter collision rates. Early results show a curious pattern. When artificial action waves are introduced, atom pairs form clusters up to 20% faster. Critics argue actions are too feeble to matter, their effects drowned out by the universe's early turbulence. But supporters counter with a cosmic coincidence. The predicted mass range for actions aligns suspiciously well with the energy scales needed to catalyze hydrogen bonding before stars formed. If future telescopes like LISA detect gravitational waves from action-driven instabilities in ancient gas clouds, it would be smoking gun evidence that dark matter didn't just lurk in the background, it rolled up its sleeves and helped build reality. The implications are staggering. If actions enabled the first molecules, they didn't just shape chemistry, they set the table for everything that followed. Galaxies, stars, even life itself might owe their existence to particles we've never seen, working in ways we're only beginning to imagine. And somewhere in the quantum static of our detectors, their whispers might still be waiting to be heard. Imagine the universe's infancy not as a smooth expanse, but as a fractured pane of glass, cracked with defects left over from the Big Bang's explosive birth. These weren't just imperfections, they were cosmic strings, hypothetical filaments of pure energy thinner than an atom but stretching across light years, vibrating with the tension of spacetime itself. And according to one daring theory, these strings didn't just warp the cosmos, they might have been the invisible scaffolds that guided the first molecules into existence. Picture these strings as celestial lightning bolts frozen in time, weaving through the primordial plasma like the threads of a spider's web. Where they passed, they didn't just bend space, they sliced through it, creating shock waves that rippled through the seething gas. In their wake, regions of slightly higher density formed, like cosmic eddies in a river. These wrinkles in the fabric of reality became the perfect cradles for chemistry, giving atoms the nudge they needed to collide and stick. Hydrogen pairs, which might have drifted apart in the uniform void, suddenly found themselves herded together by the string's gravitational whispers, their chance of bonding skyrocketing. The math behind this is staggering. Simulations of cosmic string networks show how even a single string could have created hundreds of these molecular hotspots along its length, each one a potential birthplace for the first stars. It's akin to a baker scoring dough to control where it rises, except here, the strings scored spacetime itself, directing where matter clumped and cooled. Some models suggest these defects could have accelerated molecule formation by a factor of 10, compressing what should have taken billions of years into mere millions. But the real twist, cosmic strings might have left fingerprints we can still detect today. As they vibrated, they would have emitted gravitational waves, ripples in space-time that could imprint on the cosmic microwave background. Telescopes like the upcoming LISA mission are fine-tuned to hunt for these faint echoes, which would appear as spiral patterns in the polarization of ancient light. If found, they'd confirm that the universe's first chemistry didn't emerge from randomness, but from the scars of spacetime's violent adolescence. Critics argue that strings are too exotic to take seriously, a relic of 1980s theoretical physics. Yet supporters point to eerie alignments in modern galaxy clusters, vast structures that seem to trace invisible lines as if strung along unseen filaments. Even more provocative are observations of quasars whose light exhibits unexplained frequency shifts, as though strained by the ghostly tug of long-vanished strings. Whether cosmic strings shaped our molecular origins or not, their legacy challenges us to see the universe not as a blank canvas, but as a tapestry woven with flaws that might have been the very thing that made chemistry possible. After all, sometimes it's the cracks that let the light in. We tend to assume the first molecules we detect in space are fundamental, that they represent the universe's true chemical beginnings. But what if we're seeing only a sliver of the story, filtered through an invisible bias? This is the anthropic selection principle in action, the unsettling idea that certain molecules dominate our observations not because they were the most common or important in cosmic history, but because they happen to create conditions suitable for life for us. In other words, we might be studying a universe pre-screened by our own existence, blind to chemical pathways that ended billions of years ago. Consider the rarity of molecules like water or carbon monoxide in modern astronomy. We spot them everywhere, in comets, nebulae, even distant galaxies, and assume they've always been chemical cornerstones. But what if they're merely the survivors of a much wilder molecular menagerie? Early cosmic chemistry could have birthed exotic compounds we've never imagined, structures unstable or reactive under today's conditions, vanishing without a trace. The only reason water and carbon-based molecules dominate our observations, they're the ones that didn't poison planetary nurseries or suppress star formation. The ones that, by sheer luck, allowed observers like us to evolve and notice them. This isn't just philosophical musing. The fine-tuning problem in physics where constants like the strength of gravity or the mass of electrons seem improbably perfect for life extends to chemistry. Hydrogen bonds, for example, are strong enough to stabilize DNA but weak enough to unzip for replication. Oxygen's reactivity is lethal in pure form, yet essential when bound in water. Coincidence or evidence that we're only seeing the chemical lottery tickets that paid off? Lab experiments hint at roads not taken. Under extreme pressures or temperatures, elements behave unpredictably. Nitrogen forms polymeric chains, sulfur crystallizes into metallic sheets, even sodium becomes transparent. If these alternate chemistries flourished briefly in the early universe, they might have birthed transient molecular architectures later erased by cosmic evolution. Telescopes can't detect them now, not because they didn't exist, but because the universe edited them out. The implications ripple outward. When we model the first molecules, we input physics as we know it. But what if the rules themselves were malleable in the universe's youth? Quantum fluctuations or higher dimensional leakage might have tweaked bond strengths or nuclear forces in local patches of space. Most of those regions would have fizzled into oblivion. The one we inhabit, it hit the chemical jackpot. Critics argue this veers into unfalsifiable territory. How can we study molecules that left no trace? Yet supporters counter that anomalies in the cosmic microwave background, like cold spots or swirling polarization patterns, might encode echoes of these lost chemistries. Others suggest searching for relic molecules in primordial gas clouds untouched by stellar pollution, where ancient, non-anthropic chemistry could still linger. The anthropic lens forces a humbling shift. The universe's first molecules weren't inevitable. They were contingent, a fragile sequence of accidents that, against all odds, built a world capable of wondering about them. And somewhere in the cosmic archives, alternate chemical histories might still whisper, waiting for tools we've yet to invent. What if the universe's first molecules weren't natural at all, but glitches in a cosmic simulation? This isn't just wild speculation. It's a fringe theory gaining traction among physicists who study the fabric of reality at its most fundamental level. Imagine the early cosmos as a vast digital rendering where the code underlying spacetime occasionally stuttered, leaving behind molecular artifacts like fragmented pixels in a video game. These imperfections, tiny, fleeting errors in the programming, might have been the unexpected catalysts for chemistry itself. Take helium hydride, that elusive first molecule. Its bizarre persistence in modern nebulae, despite being theoretically unstable, could be read as a cosmic anomaly, a relic from an earlier version of the universe where the rules were slightly different. Even stranger are the energy signatures of primordial hydrogen bonds, which some researchers argue align too neatly with quantized values, as if they were rendered in discrete packets rather than emerging organically. It's like finding a barcode etched into the background radiation of reality. Lab experiments add fuel to the fire. When quantum systems are simulated on supercomputers, they sometimes exhibit rounding errors, tiny discrepancies where the digital approximation doesn't quite match the expected physics. Astoundingly, similar discrepancies pop up in astrophysical data. Spectral lines from ancient gas clouds occasionally show energy shifts that defy standard quantum models. Could these be the universe's equivalent of a buffer overflow, a fleeting moment when the simulation's logic faltered? The most provocative evidence lies in the cosmic constants themselves. The fine structure constant, which governs how atoms interact with light, appears fine-tuned to an impossible degree. Alter it by even a fraction and molecules couldn't form. Simulation theorists argue this isn't a coincidence, it's a design choice, hard-coded to allow chemistry to boot up. Even the speed of light, often joked about as the universe's processing speed limit, fits eerily well with the idea of a computational framework prioritizing efficiency over realism. Skeptics dismiss this as metaphysics dressed up as science, but the debate is far from settled. If the universe is a simulation, its earliest molecules might be the equivalent of debug logs, clues left behind by the programmers. Future quantum gravity experiments could look for pixelation in spacetime at the Planck scale, hunting for evidence that reality is rendered rather than emergent. So next time you gaze at the stars, consider this. The molecules that built them might not be accidents of nature, but artifacts of something far stranger, a universe running on borrowed code with chemistry as its most elegant glitch. From the humblest hydrogen molecule to the wildest quantum foam fluctuations, we've traveled through 30 radically different visions of how chemistry first sparked in the cosmos. Each theory rewrites the cosmic origin story in its own way. Where some see randomness, others find hidden patterns. Where one model shows destruction, another reveals creation in disguise. Whether it's dark matter's invisible guidance, black holes playing molecular midwife, or the multiverse smuggling in exotic chemistry from alternate realities, these ideas don't just add branches to our knowledge, they plant entirely new trees in the forest of understanding. Think about helium hydride's fleeting existence, proof that even the most fragile bonds can alter a universe's destiny. Or ponder silicon's overlooked rain, building cosmic architecture before carbon stole the spotlight. Then there's the holographic principle, turning every molecule into a shadow play of deeper dimensional truths. These aren't just competing explanations, they're a symphony of possibilities, each instrument revealing a different harmony in the grand composition of existence. And here's what's exhilarating, we're not choosing between them. The beauty of cosmology lies in holding multiple truths at once. Maybe actions did nudge atoms together while cosmic strings plucked the gravitational fabric like a harp. Perhaps time crystals pulsed alongside quantum entanglement, weaving chemistry's first rhythms in ways we've yet to measure. The universe has never been simple. Why should its origins be? So which theory sings to you? Is it the elegant efficiency of magnetic fields sculpting gas into molecules, or the anarchic creativity of black hole radiation forging bonds in the chaos? Drop your favorite in the comments. I'm dying to hear which cosmic origin story sparks your imagination. And if this journey through primordial chemistry left you hungry for more mysteries, hit that subscribe button. We've got wormholes to explore, dark energy to unravel, and maybe, just maybe, more multiverse molecules waiting to be discovered. The universe's first whispers are still echoing, and every new theory brings us closer to understanding the language they spoke. Now it's your turn. What do you hear?